Good morning, everyone. So let's get started. So today I'll be walking you through multibody analysis with MapleSim. So innovation at the system level. So any kind of innovative designs carry risk, especially when it's time to bring any kind of complicated new parts together. So problems typically arise during prototyping, and assembly tends to be very expensive. These are known as system level issues. So if an issue that forces a design change request is not caught early in the design phases, it can cost about 64 times more than in the prototyping stage alone. And this shoots up to 200 to 800 times in the later stages, which is a drop in the bucket if this comes to light after the product is launched and forces a recall. So an example that might be familiar in general to people is cell phone battery explosions, those kind of things that hit those kind of big news type things that companies just don't want to see happen. Smaller things are that companies often are faced with is sort of motor sizing and those smaller issues, but they can be costly, and companies don't want to be faced with those issues that can be dealt with sooner in their product design. So what is system level modeling? So sometimes referred to as 1D modeling. It can also include 3D multibody dynamics, but that isn't necessarily what we'll be getting into today. This is different than models that you would make in FEA or CFD programs, which vary not only in time, but vary in spatial dimensions. System level modeling is a complementary process to these other modeling techniques. In a design process, it's generally a mix of discrete and continuous systems spanning multiple physical domains. So in a typical project, you'll have a variety of subsystems that come together to form a product, drawing from multiple domains. So mechanical, electrical, hydraulic, and others. And a system level model takes a view of these subsystems as a whole, allowing you to see interactions and behaviors that would otherwise be very hard to predict. System level modeling allows organization in the design knowledge across teams, and as we mentioned, it allows sort of that organization across teams and able to spot issues early on. And it reduces expensive prototyping iterations and error-prone reliance on spreadsheets. So why move to system level modeling? So typically, engineers that are using FEA, Excel type spreadsheets have a good sense of how their products work. They don't necessarily need a dynamic simulation, since their current tools mean that they can make basic improvements to current designs. But what happens? Skipped ahead a slide there. What happens when they significantly want to change their design? So introducing a new mechanism, adding controllers, introducing more complicated multi-domain interactions, or looking to introduce large-scale optimizations and testing into their designs. So many of the issues that come about are because design of a complex system involves several distinct distinct groups, each focused on the development of one subsystem, using dedicated tools and methods to determine if their design will comply with the specifications for that system. And once these subsystems are integrated during prototyping or even final assembly, problems arise. For example, a stress analysis of a mechanical setup will provide us with data on structural integrity and failure points. However, in isolation, such an analysis can't answer system-level questions on optimal sizing of actuators, stability of the select control strategy, or the impact of thermal management on the hydraulics. With system-level modeling, it's quick to create or test an initial concept, and it's a natural way for modeling multi-domain systems. Models where domain interactions are critical or growing, and multi-domain models are required to track down or even prevent design flaws. So ultimately, system-level modeling is a tool for innovation. So bringing this down to what we do here at MapleSoft, MapleSim is our tool for multi-domain system-level modeling and simulation. It allows you to quickly build models of complex dynamic systems by selecting and connecting components from a large library of pre-built components, covering a variety of domains like mechanical, multibody, control, thermal, electromagnetics, and hydraulics, like all of the subsystems that I mentioned previously. We also offer specialized libraries for batteries, drivelines, transmissions, tires, advanced hydraulics, and pneumatics. So MapleSim is a essentially multi-domain system-level modeling tool. It can be used for a variety of purposes within your design process. And from the perspective of catching those unforeseen design issues, MapleSim is a great tool that can help you spot those issues that arise from interactions between all subsystems in play when you're designing a product. It's also great as a design optimization tool. For example, if you're looking to figure out how big a motor needs to be, or the lifespan of a certain bearing, or you want to avoid over-purchasing or over-engineering, MapleSim can help you answer these design questions early on in the process, far earlier than a physical prototyping stage where costs start to increase. So at this point, I'm going to move over into MapleSim. So right here, I have set up a industrial pick-and-place robot. It's a system with 3 links that each has, open this up, a parameterized mass, geometry, and inertia. Each joint is driven by a motor gearbox that also is, where'd that go? That also is parameterized. If we run the simulation, we can see takes a moment. Be able to see the robot in action as it performs a task assigned to it. And system level modeling allows us to make changes to the model. We'll be able to see a variety of different outputs. So here we go. Still just finishing up. So for a complex model like this, we have a lot of outputs for analysis. Just going to jump out of here. But it allows the designer to answer specific questions about what their mechanism is doing. Okay. Nope. I'm not used to working on such a small screen today. There we go. Okay, if I run this, so we can see the tracking that our pick and place robot would follow, the motion path. So if I turn, if I move up, we can also see the path that it follows. And these are the 3 motors that I had showed you previously in the model, that those links are connected. So what this is looking at here is we have motor speed, motor torque for each of the 3 motors. If we jump out of the simulation, for the time being, I'm going to I want to show you a few different features we can do with this. So one of the things that is really nice with MapleSim, if we jump into a new model screen, MapleSim has the capability of we have a CAD toolbox, and it's quick and easy to import CAD files. So if we go File, Import CAD, I have my pick and place robot step file. If we take a look in here, there's a variety of file formats. I select this one that I have. It starts to import. And by taking a CAD file and importing it into MapleSim, we'll be able to break that apart and start to add joints in between, and all the moments of inertia, mass, and sizes are going to be available within MapleSim. So what you see here on the left are the actual top-level subassemblies and components. These pieces are going to be the parts that actually get input into our MapleSim model. We open all of these. So everything they can contain is going to be combined together into a single component. So in this case, we're going to have 4 components in MapleSim, the base, 2 arms, and the end effector. And this is essentially the same pick and place model that we just saw a very quick simulation of in MapleSim. So currently our model doesn't have any coordinates to place it in the simulation. So I can show you how we would do that. I'm not going to run through the whole entire model just for the sake of time, but I can show you just a few of them. So we zoom in. The first thing I want to do is ground it so that it's not just floating in space. So if I add my feature detector to the base, see that a coordinate is added here. If I click on that, I want to give it zeros. Apply. And we will name this one ground. Okay. The next one, I want to add, we'll start adding our connecting joints. So find here. That didn't add a joint, did it? There we go. So this one, we want it to be in our y-axis. We keep it simple. We can label this one A. Okay. And we want this one to link to this motor here. So if we copy, make sure it's the right one, and paste, this shows up here, and we have our second link. So the next one, we want to add we put another one here. And we'll keep it consistent, and we'll go with B. Come on, mouse. See, sometimes you have to be careful where you add them because they end up in places that you don't want them to. Especially when your mouse plays tricks on you, like mine is today. Maybe if I zoom in a little closer. Okay, track motor. Well, that's where they all are. I don't want them to be there. I'm going to delete those ones for now. Well, we have one connection in here. I'm going to jump ahead. I have a finished model to show you, but I can finish this one off, and I can get the CAD import to finish up. So if we hit select, it'll import it for me, and we have one connection. I can show you what that looks like. So at this point, what we can start doing once it's over in here. Lock this. This is a nice feature because I can turn that one off. I can lock them in place, and they'll stay where I want them to. So now that I have these components in here, I got a much cleaner look because of the CAD components than what I would have here in just the regular pick and place robot model. If I jump over into the fully finished model with all of the links, if I open up my for example, the base cylinder that we started adding the connections to. So here we have I got my ground. Can jump out of that. I can show you the arm connections. See, B is in there, right where it should be. But if I then run the simulation, we'll see that the model, we have the CAD model running in the simulation. There we go. And so that's just adding those same joints that I was adding. If I was as fast as one of our experts, I could probably have this done in about 4 minutes, but I'm not quite there yet. But all it takes is a little bit more practice, and the CAD import with the CAD toolbox is very fast, and it makes it look so much prettier. Okay, I'm going to close up my simulation. And open up the application. The next tool that I want to show you, if I have, is the parameter sweep. So one thing that's useful in MapleSim is we have I'm going to jump out of this just for a moment to show you the, excuse me, the full list. But we do have this list of applications and templates that provides pre-built tools to help with design analysis. So as I mentioned, I'm going to show you an example of the parameter sweep app that can be used for design optimization. So one thing, here we open this. Load system. There's one thing that can be helpful in the design process is to look at what would happen if, for example, in the pick and place robot, if you increase your load of the robot, if you want to assess your motor torque. And this application can do that for you. So I'm going to keep it all to the defaults. We can select parameters, so fast load, CPM, outputs. Where are my outputs? Just give me a moment. Apparently I did something wrong today. Something is not happy with me. Okay, let's try this again. Outputs. There we go. Okay, so let's say we take motor 1 and we look at the speed. We'll take time, max, and we'll say absolute. We'll also look at the torque on motor 1. And we'll do the same thing. We can see here, these are the ones that we've selected. And we can run the parameter sweep on those specific parameters. There we go. Here we have our results. I can look between the different displays. What I can see here. And if I choose to look at all three, my max absolute speed, mass load, and CPM, I get a 3D plot like this. One of the tools that is also helpful that can be customized. It's not necessarily something that's built in. It's more of an individual thing for each customer. For these Maple worksheets that this design tool essentially has different segments for running the simulation, has motor performance analysis, similar to before. You can look at the min, max, root mean squared, bearing loading. It's a customized tool that many of our customers have found to be useful. So we're looking at the same pick and place example. I just want to keep it. We simulate. And it has, as I mentioned, the simulation results, motor performance, and you can also export your results out of this. So what this tool uses is our Maple Core software and the Maple worksheet, and the parameter sweep is included as part of this that I was showing you previously. Jump out of this. If I can get it to run. So we have the simulation results, similar to what we saw the first time we ran the original pick and place robot. So this is just the different components, looking at speed, torque, and so on. Again, min, max, root mean squared values. We can also look at motor performance, so looking at motor torque versus speed. And we can look at the 3 different motors within the model and how they're performing. We can look at the bearings. We can export any of the above data to an Excel file. That's because I didn't export it. So now it's telling me there's an error, but that's fine. And the parameter sweep, which is the cycles per minute and mass load that I had just showed you previously, but it's performed over all parameters rather than us pre-selecting the values. So if I run this, we immediately have access to all of the different parameters to perform an analysis on those. Oh, I don't need to save those. So one quick application just to highlight for MapleSim 2018 is this 1D motion generation. I'm not going to go into detail specifically. I'm not going to run this, but I do want to highlight it as it defines signals that adhere to velocity, acceleration, and jerk constraints of the machine you're building, if it is at all relevant. This can now be done faster than in previous versions. There wasn't really a specific application or easy way to do this. But if, for example, in the pick and place robot, you're wanting to look at those constraints, there is now an application for it. Some of the other quick features are that we've updated the libraries, so model on hydraulics and pneumatic libraries, along with the CyberNet heat transfer right here. You won't see these necessarily in if you do use MapleSim already. If these are libraries that you're interested in, these can be added as toolboxes. But we've brought in more physical effects so that models you're creating will be more realistic and you'll have more opportunities to catch issues in order to optimize your designs further. It's also possible to import other component libraries and custom components, which can allow you to customize your models to a huge degree. I'm going to just jump back into PowerPoint to finish off. So the model-based systems engineering processes are being adopted by industries around the globe. And even without integrating models fully into your design chain, system-level models can yield valuable insights at many steps along the way. We think that Maple and MapleSim are just the tools to get this done, and our engineering solutions group are always available to provide all the assistance you need to take on your first system-level modeling project, whether it is your first system-level modeling project or further down the line and it's something more complex that you need help with. Our mission is to help make your engineering project succeed. They allow you to achieve more in less time, reduce project risk, and produce and share better results. So thank you for listening today.